now we are on the third lecture of basic strength. Now today we'll talk about few other compounds, few other nitrogenous bases, and we will understand how to calculate their basic strength. So first compound which we'll talk about is pyridine. So let's see how pyridine looks like. So this is the structure of pyridine, where it looks like benzene and one carbon is being replaced by nitrogen. Look at the hybridization of this nitrogen. This nitrogen is sp2 hybridized. It is sp2 hybridized. These pi bonds are in conjugation with each other and will do the resonance, whereas if I talk about this lone pair is not part of the resonance structure. This is just a standalone lone pair. So we can also call it as lone pair, localized lone pair, which is present in the sp2 hybridized orbital. It is not in unhybridized orbital, it is in a hybridized orbital, and only pi bonds are in conjugation. This lone pair will not participate in the aromaticity, it will not participate in the resonance at all. If we have to see the orbital diagram of this compound, this is how it will be. So all these are carbons here. If you see, I am showing, and the one at one place there is a nitrogen. P orbitals are in parallel to each other. This has p orbitals in parallel to each other, which are making the pi bond and doing the resonance. Whereas if I talk about this lone pair is in the hybridized orbital. So this blue one is a hybridized orbital where this lone pair resides. So this lone pair is in the hybridized orbital, which is in parallel to the plane of the compound, whereas the p orbitals are in the perpendicular plane. So this lone pair and the p orbital, which is participating in the resonance, are in perpendicular plane with respect to each other. Lone pair is in parallel plane with respect to the compound, and the p orbital, which is participating in the resonance, is on the perpendicular plane. Okay, so the lone pair is not participating in the resonance, it is in the same plane as the compound, it is not in the perpendicular plane, and it is not parallel to other p orbitals. Secondly, this is a hybridized orbital. So this lone pair, again and again I am telling you, is not the part of the aromaticity. Okay, so now look at it, how pyridine will act as a base. H plus will go attack on this pair of electron and will form this kind of bond. Nitrogen will carry a positive charge, whereas the internal pi bonds will not get affected. So aromaticity of the molecule will be still maintained. Only thing is your nitrogen will carry a positive charge. So even after your nitrogen acts as a base, it is not losing aromaticity. The lone pair is getting attacked, but that lone pair is in the hybridized orbital, in sp2 hybridized orbital. So aromaticity of the molecule is maintained even after acting as a base. Now, because this nitrogen has got a positive charge on itself, it may break the bond with the carbon what it has, that is a pi bond, and the pi bond shifts like this. So when the shifting will happen, what will happen? The electrons will be gained by nitrogen and the positive charge will come on the carbon. Now this positive charge is in conjugation with this pi bond. So when it is in conjugation with this pi bond, it will again participate in the resonance. So when it will participate in the resonance, the plus charge is also stabilized through resonance. Aromaticity is maintained, plus charge is stabilized through resonance. That is why this pyridine is a good base, because even after attacking by H plus, first of all, aromaticity is still maintained, and the plus charge what nitrogen is gaining, that plus charge is being stabilized by resonance. So here two things which are making this pyridine a good base. First, aromaticity is maintained, and second is plus charge is resonance stabilized. Now let's look at the next compound, that is pyrrole. So pyrole's formula is C4H5N. Let's look at the structure what it has. This is the structure of pyrrole, where you have a pentagon shape, or you can say it's a 5-membered ring where one atom is nitrogen. So nitrogen has a pair of electron, and that pair of electron is a delocalized pair of electron because it is in conjugation with this pi bond and this pi bond. The hybridization of this nitrogen is sp2. Let's look at the orbital diagram of it. So all the p orbitals of all the atoms, carbon and nitrogen, are in parallel to each other, and this lone pair is present in this parallel p orbital. So this is present in an unhybridized p orbital. Lone pair is in unhybridized p orbital. So when it will act as a base, basically H plus will attack here, and this will become NH2, and the nitrogen will carry a positive charge. Now look at it very carefully. Right now this molecule was aromatic before acting as a base, but now once it has reacted with H plus, it has lost that pair of electron, and now the molecule has become non-aromatic. Why non-aromatic? First of all, it is not following 4n plus 2 pi electron rule, and secondly, this nitrogen's hybridization has changed from sp2 to sp3. So hybridization has changed from sp2 to sp3, which is the condition that neither it can be anti-aromatic nor it can be aromatic, because for that the hybridization should be sp2 only. So here there are 4 pi electrons and sp3 hybridization, so the molecule has become non-aromatic. And this plus charge is not anymore stabilized through resonance. In the previous case, in the case of pyridine, the plus charge was resonance stabilized. Here the plus charge is not resonance stabilized, and that means it is not becoming stable. So from a stable aromatic system, it is moving towards a non-stable system if it acts as a base, and it is becoming a non-aromatic compound. So now if somebody asks us to compare between pyridine and pyrrole, which one seems to be a better base? Definitely pyridine, because pyridine is maintaining its aromaticity even after acting as a base, whereas pyrrole is losing its aromaticity and becoming a non-aromatic compound. So pyridine is more stronger base as compared to pyrrole. Why? Because pyridine is maintaining its aromaticity even after acting as a base. The plus charge what nitrogen is gaining is resonance stabilized, whereas in case of pyrrole is becoming non-aromatic from aromatic, and plus charge what nitrogen is gaining is not stabilized through resonance. So this is the reason why pyridine is a better base than a pyrrole. Okay, now let's do some questions on the similar concept what we have learned just now. Let's apply this concept and let's solve few questions. Now look at these compounds. You have to solve it for me. You have to tell me what is the basic strength order here. Use the logic and figure out what every nitrogen is behaving as over here. As in, like, they are part of the aromaticity, not part of the aromaticity. Aromaticity is changing, not changing. What is it? Think about it, and then I'll discuss. First, try doing it on your own. So now let's understand. So each nitrogen here has the lone pair. This nitrogen is sp2 hybridized nitrogen. Why? Because the lone pair which is present over here is a delocalized lone pair, because it participates in the resonance with the benzene. But mind it, this lone pair is not part of aromaticity. That means because of this lone pair, aromaticity is not forming. It's not that molecule is being called aromatic because of this lone pair. This is just participating in resonance. Okay, aromaticity is in the ring and is not, and will not get disturbed if H plus will attack on it. Why? Because if this molecule will get attacked by H plus, what it will look like? The benzene will still remain the benzene, and this will become NH3 plus. This is how it will be. Okay, now look at the next compound. Next compound is sp2 hybridized. There is a pair of electron over here. This is in the hybridized orbital, and this is localized lone pair. We have spoken about this. This is pyridine, and even after losing this pair of electron to H plus, or by forming the bond with H plus, it is still maintaining the aromaticity. So aromaticity is maintained here also. Aromaticity maintained. Here also aromaticity is maintained. Whereas if I talk about this compound, here this nitrogen is sp2 hybridized and lone pair is delocalized. So what will happen after it will accept the H plus? It will become non-aromatic compound. Correct? Now if I have to arrange them in the basic strength order, how does it look like? In case of second compound, what will happen? Aromaticity maintained and plus charge is resonance stabilized. Correct? Whereas in this case, in the case first, your aromaticity is maintained, but the charges are not resonance stabilized. So if you talk about more stable your conjugate acid will be, better will be your base. So second is gonna be better base than the first one. Last one's conjugate acid is definitely unstable because of the non-aromatic structure. From aromatic it is becoming non-aromatic, so it is going to be least basic. So order is gonna be second, then first, and then third. Now let's talk about this question. In this question we have taken 3 nitrogens. One is here, another is here, and third one is here. We have to tell which one is more basic nitrogen. So here in case of first, again it is very similar to the aniline one, that the lone pair is delocalized but not part of aromaticity. This one, second one, the lone pair is localized and it is not affecting the aromaticity of the molecule. So when one molecule has a delocalized lone pair and one has a localized one, which one will you say is more basic? Obviously the one which is localized. So that concept you can apply here also, that second is more basic because it has local pair of electron. In case of first, it is delocalized pair of electron. Automatically it makes second more basic than the first one. So same concept we'll apply here. Second is more basic because it is local lone pair. This is delocalized lone pair. In both the cases, aromaticity is not destroying, whereas in case of third, the pair of electron is delocalized and the aromaticity is breaking out. Aromaticity it is losing if this lone pair is being shared with the H plus. So third is gonna be least basic. Again, this is the same example. See, so these kind of questions can be asked in multiple different ways. The first question had 3 different compounds, and in the second question, the 3 different compounds have been clubbed together and has been made to a one question, but the concept is exactly same. In first one also, in case of aniline, it was delocalized lone pair, but aromaticity is maintained. In case of second, localized lone pair and aromaticity is maintained. In both the cases, aromaticity is maintained. Local one will, obviously, localized lone pair is more basic than the delocalized one. Automatically, second will become more basic than the first one. And in third one, aromaticity is getting lost. Hence, the third one is the least basic. So, same concept we are applying here also, and we are getting the same answer, second, first, and third. So this is how you have to understand the logic and you have to apply the same logic. Now let's look at the third question. In third question again we have what? We have pyridine over here and we have another compound that is quinoline. So look at the quinoline. Quinoline has this pair of electron which is again local. So we have to compare between pyridine and quinoline. Pyridine is gonna be more basic. Why? Because benzenes have minus I effect. So benzenes minus I effect will be applicable on this ring, and because of which a little withdrawal of electron will happen and will make the molecule or nitrogen lesser basic due to the inductive effect. Okay, so it has been written in the literature and this has been observed that quinoline is lesser basic, and what assumption has been made is this less basic nature is due to the benzene ring which is attached in parallel to this pyridine ring, which causes its minus I effect, and because of which little electron withdrawal happened towards the benzene chain, and that is why overall this molecule is slightly lesser basic than your pyridine one. Otherwise, both of the nitrogens are behaving in the exactly same manner. Both of the nitrogens have the lone pair localized and in the hybridized orbital and not breaking aromaticity even after showing the basic behavior. Okay. Now let's talk about the next example. Well, before we talk about the next example, let's make a small note. That small note is if you have same degree of nitrogen in a compound, let's say you have 2 compounds to compare and there is the same degree of nitrogen, then what do? Cyclic amine is more basic than your acyclic amine. For example, let's look at this molecule. Here we have nitrogen here this is the 3rd degree nitrogen. So this is the bicyclo compound, and I can write this compound like this also, right? Whereas look at this compound is also a 3rd degree nitrogen, but this is the acyclic compound. Now when we have to compare the basic strength of these compounds, what we have to look at? When you talk about any nitrogen based compound, that is amine, amines have a property of doing inversion. What do you mean by inversion? So basically their electron pair, this is my sp3 hybridized nitrogen, let's say A, B and C is present over here. So this nitrogen has a capability of doing flipping. So basically they do the inversion. Inversion means this lone pair comes down and all of this thing goes up. I don't know whether you have ever noticed or not, whether you have ever experienced this or not, but in the rain you must have seen that umbrella gets inverted. So you have kept umbrella like this. So this is your umbrella. Many a times when a strong wind is there, this gets inverted and it becomes like this. I hope you would have ever experienced this. So this umbrella gets inverted. From here it becomes like this. So this is called inversion. So exactly same thing happens. Lone pair has a tendency to go up and down, jump up and down. So this pair of electron goes down, as in like from the plane. If it is in the upper plane, it will go down. But at the same time, these bond pairs will get repelled and hence they will move up. So basically to avoid the repulsion from the lone pair, these bond pairs go up, they flip. So this molecule can flip into this molecule. So this flipping happens. This is how sp3 structure is. The lone pair will move down, so all bond pair will go up. If the lone pair goes up, the bond pairs come down. So this kind of phenomena is called as flipping. This is also called as inverted umbrella phenomena, or this is also called as flipping. This flipping is very, very important for many of the behaviors of nitrogen, what it exhibits in case of amines. Okay. Here if you talk about any open chain molecule, in open chain molecule this flipping is quite common and it always happens. The nitrogen based compound is always in equilibrium. It goes up and down, up and down, up and down, up and down. Whereas if you talk about the cyclic structure have the restriction, and because it is linked from the multiple bonds, the cyclic structure cannot do the flipping. So basically if you talk about any cycle, let's say This is how the molecule is. The flipping is not possible. In cyclic structures, so movement or the motion of the bond is restricted, and inversion doesn't happen in the case of cyclic amines. So in cyclic amines, the position of your lone pair is fixed, whereas in case of open chain amines, the lone pair position is not fixed and they keep moving from up to down, up to down, up to down. So now it is, if somebody asks me which particular compound will be more basic, the one where the lone pair is fixed or the one where the movement of the lone pair is happening and its position is changing? Obviously, the one where the position of the lone pair is fixed. So whenever such condition comes where you have a comparison between a cyclic and the open chain and the nitrogen degree is same, in that case cyclic structures will always be more basic because their pair of electron is fixed at one position. Whereas in case of open chain structures, amines lone pair or nitrogen lone pair is going to flip its position back and forth, and that is why it is not fixed at one particular position, which definitely cause some decrease in the basic strength. Okay, why? Because let's say the lone pair is down, hydrogen is attacking from up, it will not get the lone pair immediately, or the lone pair is up and hydrogen is attacking from the other plane, it will not get the lone pair. So because position of the lone pair is not fixed, and hence it causes a slight decrease in the basic strength of the molecule. So flipping, inversion in case of open chain causes a decrease in basic strength. Hence when we compare, we say that the cyclic amines are more basic than acyclic amines if the degree of the nitrogen is same. So now on this concept, let's see few questions. I have this compound here. This is my cyclic amine, again second degree of nitrogen is here. This is my open chain amine, second degree of nitrogen is here. In both the cases we have second degree amine, but here the flipping is restricted, it cannot flip, the position of lone pair is fixed, and hence this will be more basic than this one. Look at this compound now. Now in this compound I have a tertiary amine over here, and here also I have a tertiary amine. Hence flipping is definitely restricted in both the cases. So what will be a deciding factor over here, that which one will be more basic and which one will be less basic? So now here understand this thing. Whenever we have two nitrogens in the compound, we only consider one nitrogen for calculating the basic strength. Other nitrogen will only be doing or only be showing minus I effect, that's all. So we will consider the minus I effect of nitrogen. If there are two nitrogens, one will be acting as a base and another will be just imparting the minus I effect on the whole molecule. So minus I means electron withdrawing effect. So here I have one nitrogen present over here, which is definitely withdrawing some electron density from the compound, and that electron withdrawal will be experienced by this nitrogen also, and hence overall basic strength will be lesser in this case as compared to this. Let me explain you this again. Here we have two nitrogens, both have the same degree. Let's consider this nitrogen and this nitrogen for the basic strength comparison. Both are 3 degree. In both the cases, the movement of the electrons is restricted, or you can say the rotation or flipping is restricted. So which one will be the less basic? The one in which there is another nitrogen present, because this nitrogen will show a minus I impact on another nitrogen, and hence will overall decrease the electron density in the compound as well as on the other nitrogen, and hence will decrease the basic strength. So this second one is going to be more basic than the first one. Now let's compare this compound also. In this compound again we have third degree nitrogen here. There is a third degree. This is open chain. This is closed chain. So in closed chain flipping will not happen, whereas in this case flipping will happen. That means the first compound is going to be more basic than the second one. And why is it so? Because the electron availability is more easy in case of the first compound than the second one, because it is fixed at a particular position. Now let's discuss about the next compound, that is amidines. So this is our amidine, where you have RC double bond NH single bond NH2. So here we have two nitrogens, one here, one here. Look at these two nitrogens. This nitrogen has a pair of electron as well as this nitrogen has pair of electron. Let's assume this is Y and this is X. Let's talk about the behavior of these nitrogens. So this nitrogen which is present over here at Y, this is your sp2 hybridized nitrogen, and the lone pair here is delocalized. Why? Because this is in conjugation with this pi bond. Correct? Now look at the X nitrogen. This lone pair is localized because it is not in conjugation with anything, and this pair of electron or this nitrogen is also experiencing the plus M effect due to this nitrogen. The nitrogen which is present over here, this Y nitrogen, is giving its electron density on the compound through resonance, and hence this nitrogen is experiencing the plus M effect of Y. Right? So we have to understand which is more basic. Definitely your Y has a delocalized pair of electron, whereas your X has a localized pair of electron. Localized one should definitely be more basic than your X. Why? two reasons. One is the localized lone pair, second is plus M. Plus M means donating effect of Y is coming on the nitrogen here. So this nitrogen has a local pair plus some electron density coming from Y, which is making this nitrogen very electron rich, and hence this X should be more basic than Y. There is other way also to understand this concept. One is through this, directly looking at it and understanding how each nitrogen's behavior is in this molecule, and then what all different effects it is experiencing, and then mentioning it right here. Or the other way is make its conjugate acid and see whether it is stable, less stable, more stable. More stable your conjugate acid is gonna be, stronger your base is gonna be, right? So let's do it other way by reacting it with H plus. So if H plus will attack on Y, then in that case this is how your species will look like. This will become NH3 plus and this will remain NH. So this is one molecule, right? Here this plus charge will get stability, whatever it will get from this NH and all that. I mean, whatever the normal phenomena is through resonance, this plus will be resonance stabilized through this pi bond. That's all. Because it is in conjugation with this pi bond. If this H plus will attack on this NH, which is at X position, in that case this will become NH2 plus. If this will become NH2 plus, look at it, this nitrogen will show its plus M effect, will give its electron density here, and this pi bond will break, and this is how the species will become. This will become NH2 plus and this will become NH2 with a pair of electron. Again, look at it here, R, C, double bond NH2 and plus single bond NH2 and pair of electron. This is my molecule is. This will give its electron density here. This will bring it here. So what the species will look like? This will form a pi bond here. This will become NH2 plus, then single bond, then NH2 and then pair of electron. This is what it will form. Isn't this same as this? So basically resonance is happening and it is forming two equivalent resonating structures. Once it will form two equivalent resonating structures, automatically this conjugate acid is going to be much more stable than the previous one, right? So this X position is more basic than your Y position because its conjugate acid is much more stable, much more resonance stable as compared to the Y one, right? So if you ask me the basic strength order of X and Y, X is more basic than Y, or X nitrogen is more basic than the Y one. X is more basic than the Y one. Right? This is about the nitrogens of amidine. Let's talk about another compound, that is guanidine. So next is guanidine. So guanidine is actually the strongest organic nitrogenous base, but it is definitely weaker than all the other inorganic hydroxylic bases. But among the organic nitrogenous bases, this is the one which is the strongest base. How the structure looks like? This is the structure. C, NH2, NH2 and double bond NH. This is your guanidine. So here you can have derivatives of it by replacing hydrogen with any R group. That is also possible. So different guanidine derivatives are also possible. This is the smallest, or this is the, you can say, simplest structure of guanidine. Now here we have three nitrogens. Let's mark them X, Y and Z. Three nitrogens are there and we have to understand which one is more basic. So again, see, this nitrogen's electron pair and this nitrogen's electron pair are, these both nitrogens are sp2 hybridized nitrogens, and lone pair is delocalized, participating in the resonance. Look at the molecule structure very carefully. This lone pair is in conjugation with this pi bond. This lone pair is in conjugation with this pi bond. So both are in conjugation with the pi bond. Whereas if you look at the X pair of electron is localized. Correct? This is sp2 hybridized nitrogen, localized lone pair, and so this nitrogen is getting plus M effect of this nitrogen as well as plus M effect of this nitrogen also, because these nitrogens are donating their electron density because they are in conjugation with this pi bond. So donation of electron is happening by Y and Z towards X, and hence so this X nitrogen is getting plus M stabilization, or you can say plus M electron donation from Y nitrogen as well as Z nitrogen. So where is the electron dense situation? Both the ends, no matter you talk about Z or you talk about Y, both are donating, and this is at the receiving end, as well as this pair of electron is local pair of electron on X. So hence there is it is extremely electron rich nitrogen. So if somebody asks me what is the basicity order here, this is definitely most electron rich. So X will be most electron rich and Y and Z will be equally electron rich, or you can say equal bases, because both are exactly same. Both have the exactly same configuration in the molecule. As I mentioned before, this can also be explained through its conjugate acid stabilization. So what we'll do is we'll attack hydrogen at each and every nitrogen and we'll see how their cations are formed. Let's suppose this H plus attacks on this nitrogen, this is Y. Then it will form this species and plus charge is present over here. So this plus charge is present over here. Now see if this H plus will attack here, which is Z position, this will form NH3 plus C double bond NH and NH2. Again, this is the same species, so they have the same cation forming. What will happen if this H plus will attack on this X? Let's see in the next slide. If this attack is happening on X, this will form NH2 plus, and this plus charge is resonance stabilized with these pair of electrons. So these nitrogens will show their plus M effect, and this will form like this. So plus charge will come over here. This is one resonating structure, correct? Or this can also happen that this donates its pair of electron and this becomes this. So in that case, this will be here will be your plus charge and this will be your structure. Now look at these three structures. All of these three structures are equivalent resonating structures. So three equivalent resonating structures are forming when the attack of H plus is happening on X. So the cation which is forming after showing the basic behavior is extremely stable due to the formation of three equivalent resonating structures of the cation formed. Now, what will be the basic strength order? Obviously, the most stable cation is the cation of X, hence X nitrogen is most basic, and Y and Z are equivalently basic. I think I have done a mistake over here. It should be X, then Y is equal to Z. So, Y and Z will have same basicity, whereas X will be most basic. And that is due to the nitrogen which is doubly bonded, that is getting plus M effect of two nitrogens forming equivalent resonating structures. This is causing the extreme stability to the cation forming on the X position, and that is the reason of this guanidine being most strong nitrogenous base in case of organic compounds. When we talk about guanidine and amidine, both of these compounds, guanidine is more stronger base than the amidine, though both have the similar structures, but three equivalent resonating structures are forming in guanidine. Two equivalent resonating structures are forming in amidine. That is the reason amidine you call it, or amidine you call it, whatever you want to call it, you can call it. But that is the reason why guanidine is more stronger base than your amidine. Now let's check an example. So I have an example over here. Look at this compound. This is the guanidine derivative. Instead of hydrogen, there is a CH3 over here. This is again amidine derivative here. Instead of hydrogen, you have CH3 over here. I think I have missed writing a hydrogen. So here hydrogen is also there. And this is again amidine derivative. So if I have to arrange them in the basic strength order, as I mentioned, guanidine is going to be the most basic one because three equivalent resonating structures are forming for this nitrogen. Right now, among these two amidine derivatives, what you have to see, there is a CH3 present over here and present over here, which are more electron donating. So more electron donating means these are making the nitrogen more electron rich, and this is gonna be more basic, and this is gonna be the least basic. So second is lesser basic and third one is the least basic one. Now let's talk about the next compound. In this compound again we have, this is a guanidine derivative. Look at it. So this is your R group, and this is the guanidine configuration, the setup how it is. This is your amidine, again the R group is here, and this is how the amidine molecules group arrangement is. This is your normal sp2 hybridized NH present over here, and here NH2 which is sp2 hybridized. The lone pair is delocalized lone pair because it is in conjugation with this pi bond. This double bond is a localized lone pair, but this nitrogen is sp2 hybridized nitrogen. If we have to arrange them in the basic strength order, the most basic one is guanidine, then your amidine. Now out of these two, this is local one, the lone pair is local, hence it will be more basic. This is the delocalized lone pair, hence it will be the least basic one. So the order is going to be 1, 2, 3 and 4. So that's how we find out the basic strength order even for the difficult looking or bulky looking nitrogen based compounds. Now I have written a basic strength order over here in general. If you remember it, if you understand this, it will be easier for you to arrange the compounds in their basic strength order. So most basic will be your guanidine compounds, then your amidine compounds, then comes your normal aliphatic amines, that is secondary, tertiary, primary. In this order we have already discussed that the aliphatic amines are arranged in this order only if R is not equivalent to Me. If R is Me, then the order becomes secondary, primary and tertiary. Then comes your amine, then comes your pyridine, then comes your aniline, and the last is your pyrrole. So pyrrole has the least basic strength among all. So this is your basic strength order. If you remember this, it will be very, very easy for you to arrange the compounds in their basics, in their basicity order, in their basic strength order, pKb order, Kb order, whatever is asked in the question. Now, the last and the least basic compound is your amides. So when you talk about amides, why amides are least basic, let's understand. Amides are least basic. Why? Because in amide there are two electronegative atoms. One is nitrogen, another is oxygen, and the resonance happens in such a way that nitrogen gives away its electron density to oxygen and oxygen gets a negative charge. So basically, when we talk about the basic strength order, we talk about the nitrogenous basis. So we are basically talking about nitrogen, that whether that nitrogen can act as a base or not, whether that nitrogen can give its pair of electron to something else or not. But here, instead of nitrogen, oxygen is much better base. Oxygen is a better basic center than nitrogen. So if we are comparing only nitrogen, if we are talking about the nitrogen being acting as a base, nitrogen is a weak thing over here because oxygen is a better element here which can act as a base, not nitrogen. Nitrogen will give away its density in the compound itself and will acquire a positive charge. And because it is a positively charged nitrogen, not very easily it can give away its electron pair to anything else because that electron pair has got shifted to the oxygen. So oxygen is a better basic center in the molecule. When you compare the bases, you basically compare the strength of nitrogen over there, and strength of nitrogen here is very, very weak, right? Moreover, there is one more small thing. When you have pyridine present, and pyridine has an electron releasing group on it, then it becomes little more basic than ammonia, unlike what is written in the order. In order, I have shown you that NH3 is more basic than your pyridine, but if any electron releasing group is present on the pyridine, then automatically it becomes better base than your NH3, and this is all through observation. So all these things you have to remember. This is very important. This will help you in solving all different type of questions what can be asked in the basic strength order. In next class, we'll talk about different compounds. If have been given there are multiple nitrogens there, how will you choose which nitrogen will act as a base, and how will you do the H plus attack on a specific nitrogen? And we will talk about the feasibility of the basic reactions. That's all about the basic strength, and we'll be done with the basic strength series altogether. So next is the last class. We'll be talking about how to choose the nitrogen for a basic attack or H plus attack, and then the feasibility of some reactions or feasibility of some basic reactions. That we'll be discussing in the next class, and basic strength will be order. After that, we'll be talking about tautomerism, and GOC is over. So you watch this video, ask me whatever doubts you have. Watch it at a faster speed if you are able to understand, or if you find this video slow. If you are not able to understand it in a one go, repeat multiple times, watch it and ask the doubts in the next class.